This is a truly tantalizing image. Why is it tantalizing? Since its discovery over 100 years ago, it has captivated astronomers the world over. It lies so despairingly close, yet would take generations to reach. It's not visible to the naked eye, yet it is the closest star to our solar system. It was at one point the lowest luminosity star known to man, yet also the most active one. As if the paradoxes of this star weren't alluring enough, scientists have recently discovered a seemingly Earth-like exoplanet in its orbit, opening conversations about interstellar colonization that include Mark Zuckerberg, Elon Musk, and Stephen Hawking. It's almost like it is knowingly toying with us humans and our unquenchable curiosity for what lies beyond. If you're anything like me, you also can't wait to drink in everything there is to know about this enigmatic star. I'm Alex McColgan and you're watching Astrum. Join me today and let's indulge in a whistle-stop tour of the Alpha Centauri star system, from the binary stars Alpha Centauri AB to diving deep into everything we know about Proxima Centauri, its recently discovered planets, a controversial possible discovery, and what kind of flyby missions the future might hold. Leaving Earth, it would take just over 4 light years to reach the closest known stars to our solar system. I say stars because they are technically a triple star system. Collectively known as Alpha Centauri, they are made up of Rigel Kentaurus, also known as Alpha Centauri A, Ptolemy, also known as Alpha Centauri B, and Proxima Centauri. Together, Rigel Kentaurus and Ptolemy make up the binary star system Alpha Centauri AB. They sit 4.37 light years away from Earth and are both sun-like stars orbiting a common center every 79.76 years. If you're south of the 40th parallel, you'll be able to see them at night, though to the naked eye, they'd look just like a single star. The third brightest in the sky behind only Sirius and Canopus. The binary Alpha Centauri system was discovered in 1689, but it would take over 200 years for the third star to reveal itself. Luck came in 1915 to a Scottish astronomer named Robert Innes. At the time, Innes was the director of the Union Observatory in Johannesburg, South Africa. While comparing photographic plates with the help of a blink comparator, he observed that a faint star had moved in the 5 years between photos. This movement was about the same as that of the Alpha Centauri binary star he was observing. He wondered if the new star could be part of the same system. After further investigation, he concluded that it was closer to the Sun than its twin siblings, a finding which was quickly confirmed by its contemporaries. Paradoxically, it became both the closest and dimmest known star at the time. The surprises didn't end there. In 1951, American astronomer Harlow Shapley discovered that Proxima Centauri is a flare star. Not only that, but it was the most active flare star known back then. Over the last 70 years, Proxima Centauri has become a hotly studied star, no pun intended. And with the recent discoveries of an Earth-like exoplanet orbiting it, I think that interest will only intensify. But I'm getting ahead of myself. Let's get to know this star a little better before placing such grand expectations on it. At 4.24 light years away, Proxima Centauri is slightly closer to us than Alpha Centauri AB. It is a main sequence red dwarf star with an estimated mass of 12.2% and a diameter of 15% that of our Sun. Despite its smaller size, Proxima Centauri is about 40 times more dense than our Sun. Due to its low mass, the interior of the star is totally convective. This creates a magnetic field around the star and leads to the sporadic release of this magnetic energy in the form of flares. As a result, Proxima Centauri randomly experiences drastic changes in brightness and energy emissions. On the 6th of May 2019, a flare event on Proxima Centauri was observed as being the brightest one ever recorded. These flares release radiation across the electromagnetic spectrum, including X-rays. To give you an idea of Proxima Centauri's solar activity, its baseline X-ray luminosity is roughly equivalent to that of our Sun, a much larger and hotter star. This level can increase by up to 2 orders of magnitude during a flare. Not only does Proxima Centauri have more intense solar activity than our Sun, it also has a higher frequency of it. It is estimated that 88% of the star's surface is active at any given time. This is way higher than our Sun, even at the peak of its solar cycle. But before you start thinking of Proxima Centauri as a fiery ball of fury, remember, we are comparing apples and oranges here. Our Sun is not a red dwarf. In fact, compared to other red dwarfs, Proxima Centauri is considered to have a low activity level. Unlike the Sun, which scientists estimate will only burn through 10% of its hydrogen supply before burning out, Proxima Centauri is predicted to use up almost all its fuel before leaving the main sequence in about 4 trillion years. And by then, Earth, our Sun, and our whole solar system will be long gone. Alpha Centauri AB is 0.13 light-years or 2 trillion kilometers away from Proxima Centauri. You may be wondering, if Proxima Centauri is so far away from its companion stars, why is it considered part of the same stellar system? Well, we have data that shows it is gravitationally bound to the Alpha Centauri AB binary star, making it part of the stellar system with an orbital period of about 550,000 years. How it ended up in this orbital situation is still open to speculation, but the 2 main scenarios seem to be either 1. Proxima Centauri was bound to the Alpha Centauri system during its formation, meaning the stars likely share the same elemental composition, or 2. Proxima Centauri was captured by the binary star's gravity during an encounter, leading to a highly eccentric orbit that was later stabilized by the galactic tide and further stellar encounters. Regardless of how Proxima Centauri got into this triplet, calculations suggest that in 3.5 billion years it will get out. As Alpha Centauri AB continues to evolve and lose mass over its lifetime, Proxima Centauri will unbind from the system. The binary star system itself is also predicted to disassociate and diverge in about 12 billion years into 2 white dwarfs, which will forge independent and steadily diverging paths. Being our closest neighbors, we know quite a lot about Alpha Centauri AB, but we'll go into more detail about this binary star system in another video. For now, it's all eyes on Proxima Centauri. The search for exoplanets around Proxima Centauri had been ongoing since the mid-2000s, without much luck. But researchers weren't willing to give up. Not only was this star the closest neighbor we had, it was also a red dwarf, 20 to 40% of which have a planet orbiting in a habitable zone. The patience paid off. Observations at the European Southern Observatory in Chile identified anomalies in Proxima Centauri which couldn't be explained by flares or other solar activity. The data seem to indicate there may be a planet orbiting it. In January 2016, the Pale Red Dot campaign, a coordinated effort from multidisciplinary scientists and ground-based telescopes around the world, was launched to see if this suspected planet could be identified. In August of the same year, the discovery of exoplanet Proxima Centauri b was announced. It is at least 1.07 times larger than Earth, and sits 20 times closer to Proxima Centauri than we do to our Sun. This exoplanet orbits its star in just 11.2 Earth days. Even though Proxima b is within Proxima Centauri's habitable zone, that's not to say it could sustain life. There's lots of other factors that determine habitability than liquid water. For one, the intense solar activity would pelt the planet with 10 to 60 times the amount of UV and X-ray radiation we get here on Earth. We'd need to develop SPF 3000 to make the journey worth it. Another factor to consider is whether an atmosphere could survive under such conditions. As far as we know, atmospheres are vital for the maintenance of a water-friendly surface pressure, protection from dangerous space weather, and planetary climate regulation. The radiation Proxima b is exposed to might be enough to strip away the key components of an atmosphere over time. Frustratingly, we don't know much about Proxima b beyond its distance from its star and its orbital period. It is unlikely to have any moons due to the instability of their orbits over larger timescales, but it is thought the planet itself is tidally locked to its star. As discussed in a recent video, this doesn't bode well for potential habitability. It also likely developed under extremely different conditions from Earth. Assuming it formed at the current distance from its star, it would have gone through a much faster evolution, with stronger impacts and less water. However, there is some debate about its formation. Some scientists think the amount of material in the protoplanetary disk would be insufficient for it to form at its current distance from the star. It's more likely, they say, that the planet formed farther away from its star and eventually drifted into its current orbit around Proxima Centauri. What the surface of the planet might look like is down to pure speculation. Theories range from a planet covered in ice to planet-wide oceans like Earth, though unlikely if the planet is indeed tidally locked, to a water-free world with only dry land, or a subsurface ocean like Europa. In short, no idea. We haven't directly imaged the planet yet, so we'll have to wait for the first flybys to get a better idea, which some moguls are already planning. If it happens, I have a feeling it will be just as earth-shattering as the Voyager flybys in the 70s and 80s, but more on that later. 6 years after the discovery of Proxima b, the news of Proxima d swept global headlines. The first signs of the planet emerged in 2020, when a weak 5.15 day signal was detected in the radial velocity data during a study of Proxima b's mass. Following further data collection and analysis, scientists announced the discovery of Proxima d in February 2022. So far, we know it's a sub-Earth planet with at least 25% the mass of Earth, orbiting the star every 5.1 days. Sitting at a distance of 4.3 million kilometers, it orbits too close to have a habitable equilibrium temperature, which would be driven up to 87 degrees Celsius. It's also probably tidally locked, and would be pelted with so much radiation the chances of finding life there are very slim. But this planet holds promise in another realm. It is the lightest planet to ever be detected with the radial velocity method. Since the planet is too far to be seen with telescopes, scientists rely on a characteristic wobble anomaly in the movement of a star that indicates the potential presence of a planet. The more massive the planet, the more obvious the wobble. In the case of Proxima d, the wobble was practically imperceptible. To me, the fact that we caught the wobble and were then able to demonstrate with enough certainty that it is caused by a planet is a technological milestone worth celebrating. If only the world of astronomy were so cut and dry. Where there is breakthrough and celebration on one hand, there is bleak uncertainty on the other. That's exactly where you'll find the controversial exoplanet Proxima c. Initially detected in 2019 using the same radial velocity method that found Proxima d, the existence of Proxima c was then confirmed in 2020 using Hubble astrometry data. However, in 2022, another team challenged the initial radial velocity data that led to the alleged discovery. They claimed the anomalies could have instead been associated with small, unaccounted systematic errors in the data extraction method the researchers used. Basically, a miscalibration. The trouble arises from the fact that, unlike Proxima d, which orbits incredibly close to the star, the data for alleged exoplanet Proxima c places it very far away from its star, with an estimated 1,928-day orbit. There is no similar example of a wobble detection of a planet with such a low amplitude at such a long period. That doesn't necessarily mean it's wrong, but it's going to require some confirmation from additional observations, says Paul Robertson, astronomer at University of California, Irvine. If Proxima c does exist, it will take a bit more data to convince reluctant skeptics. If it does not exist, it remains unclear why the Hubble astrometric data was able to corroborate and confirm a planetary signature. I guess we'll just have to wait and see what future studies find. With the recent discovery of Proxima b and how relatively close Proxima Centauri is to us, it is a perfect candidate for a future flyby. However, reaching our neighbouring star system will take thousands of years using conventional propulsion technologies. Newer techniques like solar sails or nuclear propulsion might make such a trip possible within a human lifetime. Such ideas spearheaded the development of Project Breakthrough Starshot, an initiative set up by investor and physicist Yuri Milner, which aims to reach the Alpha Centauri system within the first half of the 21st century. The idea is to conduct a flyby mission by sending microprobes weighing just a few grams at 15 to 20% the speed of light, and they think they could do it as early as 2036. With this timeline, the probes would reach Alpha Centauri in 20 years, and we on Earth would receive the first data 4 years later. After the initial flyby, the probes would possibly venture to the exoplanets and collect data on their atmospheric compositions, much like the Voyager missions did on our outer solar system decades ago. The team is pinning their hopes on the yet-to-be-developed Star Chip, a microelectronic gram-scale wafer carrying cameras, photon thrusters, power supply, navigation, and communication equipment, essentially constituting a fully functional space probe. This is based on Moore's law, which states that the speed and capability of computers can be expected to double every 2 years. Bold and ambitious, the plan is not without its challenges. The team proposes to power these microprobes with 100 gigawatts of Earth-based lasers. That's the equivalent of the output of 100 large nuclear power plants concentrated on probes just centimeters wide. Plus, all components of these tiny probes must be built to withstand extreme acceleration, cold, vacuum, and collisions with space dust. With this in mind, perhaps the project would more aptly be named Project Breakthrough Longshot. But if the history of space exploration has taught us anything, it is that missions confronted with cruel hardship and slim odds can emerge as triumphant milestones of humanity. Proxima Centauri might just be the next one for the history books. Let's just hope we are around to see it. As telescopes like the James Webb look out across the Milky Way, you might have heard the growing buzz around newly discovered exoplanets. It wasn't that long ago, only 1992, that we found the first planet outside our solar system. But since then, over 5,500 have been confirmed in the relatively small area of space, only a few thousand light years across, that we reside in. When the Milky Way itself is roughly 100,000 light years in diameter, this offers us a tantalizing promise of billions to trillions more across the rest of our galaxy. Every star, on average, likely has at least one planet, and perhaps has several. With all of these exoplanets out there just waiting to be found, it's only natural we would want to turn our thoughts towards Goldilocks zones and planet habitability. After all, humanity has its eye on colonizing the stars, and an Earth 2.0 is surely waiting for us out there, mathematically speaking. In fact, you might have already heard that phrase, Earth 2.0, being delivered in headlines of articles or videos claiming that a planet has been discovered that would be ideal for human life and colonization. However, don't believe the hype. All the planets we found so far have, to put it scientifically, sucked. And once you hear what I'm about to tell you, you'll agree that moving to any of them will be the last thing any sane person would want to do. I'm Alex McColgan, and you're watching Astrum. Join with me today as I give you the grand real estate tour on the potential Earth 2.0s we've discovered so far, and explain why right now is the wrong time to get onto the planetary property ladder. When choosing an Earth 2.0, just like with building a house, it's a good idea to start by establishing your non-negotiables. Some of this is fairly simple to consider. For instance, temperature. You want a nice, temperate climate, somewhere that's not too warm and not too cold. Given that temperature drops the further you are from the sun, every planetary system has a sweet spot where the temperature of a planet is likely just right. Not too hot and not too cold, similar to Goldilocks and her bowls of stolen porridge. As a rough rule of thumb, if a planet is at the right distance from a star, it may well have a suitable temperature for us to set up shop. Of course, this is in no way a guarantee. After all, Venus, a planet residing in this zone, in theory should be perfect, but its choking atmosphere makes it the hottest planet in our solar system in spite of its relative distance from the Sun compared with Mercury. So it's clear, atmosphere also plays a part in all this. Speaking of atmosphere, that's also something you'll want to look for on Earth 2.0. Ideally something with oxygen and water vapor, and without anything that would poison us, but at least something that could trap heat in and offer some protection from space radiation. However, sometimes a non-negotiable is simply the neighbors that live close by. So let's consider the first major reason why most of the galaxy's exoplanets fall short: their neighboring stars. Our own star is known as a G-type yellow dwarf, a relatively fast-burning, short-lived sort of star, at least compared to some of the other options out there. Stars like our Sun tend to live for 10 billion years before their cores collapse and they transform into a red giant. It is stable, and that stability has been useful for the life that eventually flourished here. However, yellow dwarfs are far from common in the Milky Way. They represent only 10% of the total stars. Far more common in occurrence are the long-lived red dwarfs, which make up 75% of the stars in our galaxy and can live for around 14 trillion years, longer than our universe has existed, which means we've never seen one die, so to speak. And unfortunately for the planets orbiting them, red dwarfs come with numerous drawbacks. For starters, red dwarfs have a much closer Goldilocks zone compared to their yellow cousins. They burn less brightly, with luminosities between 10% and a measly 0.0125% that of our suns. So unless you want to live on a world shrouded in perpetual night, which sounds cold and depressing to me and will make growing plants a bit of a challenge, you'd want an Earth 2.0 to be a lot nearer to its red dwarf to compensate. This wouldn't be in and of itself a problem if it weren't for the second characteristic of red dwarfs that make them very unpleasant neighbors: their instability. Our Sun is the main source of our space weather. It shoots out a frequent stream of solar winds, flares, and coronal mass ejections. However, this doesn't compare to the amount of space weather created by red dwarfs. Flares from red dwarfs can be 100 to 1,000 times more powerful than those emitted by our Sun. The frequent bursts of plasma and radiation coming from red dwarfs are powerful and dangerous enough to strip away the atmosphere and even boil liquid water on planets in the habitable zone. And given how much closer planets are to their star in a red dwarf system, the odds of life getting enough time to arise before being hit with a life-sanitizing dose of X-rays is pretty slim. If you want to live on a planet around a red dwarf, you'll likely need some serious sun cream. This rules out many known exoplanets, such as astronomer favorite Kepler 186f, which some scientists hoped might be habitable. while it may be possible to live for a time in quite uncomfortable conditions in a deep underground bunker on such a planet, the experience would hardly be pleasant. But even during periods between harsh solar weather events, there's another problem with planets around red dwarfs: their tendency to be tidally locked. Being tidally locked means that the same side of the planet always faces the star as it orbits. There is no rotation between day and night. One side of the planet is in perpetual heat, and the other side in permanent shadow. Due to gravitational constraints, planets near their sun have a tendency towards being tidally locked. Just take a look at Mercury with its day that lasts 176 Earth days, or 2 Mercurian years. This lack of rotation could render most of the planet uninhabitable. You'd either face scorching desert creating heat on the day side, or freezing ice on the night side. Even if humans tried to live in the narrow band of twilight that would ring a tidally locked planet, liquid water might prove difficult to find. Any moisture in the air that found its way to the night side of the planet would get locked there, solidified as ice. Overall, the planet would be very dry, and even in the twilight zone, there would be no rain. And that's not to mention the low power of a magnetic field that would likely be found on a tidally locked planet. The dynamo effect that powers the magnetic field on Earth is thought to be influenced by the Coriolis effect, the rotation of the Earth imparting momentum to rising and falling liquid metal in its core. Without this rotation, such a magnetic field would be inevitably weaker. So, I'm sorry to say that this rules out planets such as Proxima Centauri b, our closest exoplanet. Proxima Centauri b is otherwise an interesting candidate. Its closeness makes it one of the easiest planets to get to for us, situated only 4.2 light years away. It's thought to be a rocky, Earth-like planet, which is convenient, as living on a gas giant would be challenging to anyone with a fondness for solid floors beneath their feet. And most compelling, its mass and radius are very similar to Earth's, meaning it has a similar gravity. Why is this important? Let's compare it with another Earth 2.0 contender, Kepler 452b, the first planet to ever be referred to by that title, and the planet described by a NASA scientist as the closest twin to Earth. Kepler 452b has much to recommend it. It is orbiting around a yellow dwarf, like us, at a similar distance. This means it's in the Goldilocks zone that makes liquid water on the surface possible. However, it is a super Earth. This means it has a mass and radius combination that makes it about twice that of Earth's. When it comes to gravity, how much is too much? Some scientists researching the question put the figure at 4 times Earth's gravity, this being about the limit of what a human could survive. However, even living in just twice Earth's gravity could get rather uncomfortable. To properly visualize this, or at least get a rough approximation of it, imagine lying down, but then imagine a second person lying on top of you, putting all their weight on you. This is your night. Every night. Every breath being fought for. Come daybreak, you must lift that extra person up, haul them onto your back, and then carry them with you everywhere you go. Everywhere. And be careful not to fall, as suddenly it's much easier to break a bone. Falling downstairs is no longer painful, it's likely lethal. Everyone must do this. The elderly, the infirm, small infants trying to take their first wobbling step. Keeping this in mind, it's easy to grasp just how exhausting life in double gravity might end up being. If you're a bodybuilder or athlete, you will likely be alright, but for most people on Earth, it would be a slow torture. Your heart furiously beating to move your blood around, making it feel like you're running even when you're standing still. And if you want to triple the gravity, add an additional person on top of that. And things don't get much better going the other way. Sure, everything is much easier as that weight is lifted, However, living under reduced gravity comes with a host of health risks that we can see from astronauts who've spent just a few months on the International Space Station. Over time, the calcium bleeds out of your bones, causing them to become brittle. Your muscles atrophy. Your heart develops issues. Your immune system suffers. All told, even if you're exercising every day, your long-term prospects aren't looking good in a low-gravity environment. A fact that is challenging NASA scientists as they try to figure out how to set up human outposts on places like the Moon or Mars, where astronauts might go to live for just a few years. Humans have spent millions of years adapting to life on our planet. We're very used to how things are here. We're just not suited to anywhere else. We've not evolved to face such conditions. In some respects, it's a testament to how well we've acclimatized to the environment we were born in, but it's a big obstacle if ever we want to live anywhere else. And so, the hunt for Earth 2.0 goes on. As I mentioned, there are likely billions of undiscovered planets in our Milky Way galaxy. The odds of at least one being out there that meets our criteria for gravity, temperature, lack of life-threatening radiation, and presence of atmosphere and water are high enough to be a certainty. Actually finding one that meets the criteria is much more of a challenging task, particularly when most planets are still invisible to even our strongest telescopes, except for a brief moment when they pass in front of a convenient star and block out its light. If someone tells you that they've already found Earth 2.0, I take it with a pinch of salt. We won't ever really know that the planet is actually suitable for human life until we somehow cross the gulf of space and go there to see it in person. Of course, until we discover how to do that, it's all a bit of a moot question anyway.
How can a blurry image of a star help us understand more about their orbiting exoplanets than a clear, sharp image? It seems counterintuitive, but that's exactly what CHEOPS, or the Characterizing Exoplanet Satellite, is doing. CHEOPS is a space telescope launched by the European Space Agency in December of last year, with a mission to hunt down the most Earth-like exoplanets, which, as you can probably imagine considering the distances involved, is not an easy feat. I'm Alex McColgan and you're watching Astrum, and in this video we will talk about the very promising ESA mission CHEOPS. This video is a collaboration with our Spanish channel, Astrum Español, which you can find a link to here and in the description. Please show Rafa, our Spanish host, some support. I think he's doing a great job, and if you're a Spanish speaker, make sure to take a look at his channel. CHEOPS is a joint effort with ESA and the Swiss Space Office, which is fitting as it was Swiss astronomers who discovered the first exoplanet back in 1995. It's hard to believe, given that we now have confirmed the existence of thousands of exoplanets, but it was only 25 years ago when we discovered the first one, so we are still in the early days of this astronomical field. The planet they discovered is now called 51 Pegasi b, or Dimidium, a gas giant around 50 light-years away in the constellation Pegasus. It is now considered the prototype for what has come to be known as hot Jupiters. These planets are similar in size to our gas giant neighbour, but orbit their planet star very tightly, some with orbital periods of 10 days or less. This means they are extremely hot due to their close proximity to their sun. The reason exoplanets are only just being discovered is because they are exceptionally difficult to observe, as they are hidden by the brightness of their stars. That's why we have to really think outside the box if we want to detect them. If you use a regular telescope to look at stars that are known to have exoplanets orbiting them, you'll only see the shine of the star, as its brightness compared to any close orbiting exoplanet is overwhelming. You can't even directly see exoplanets around the closest star system to us, Alpha Centauri, which is only 4 light-years away from us. If that is our closest neighbour, and directly observing through a regular telescope won't work, imagine trying to observe exoplanets tens to hundreds of light years away. So how did those astronomers discover Dimidium? Well, hot Jupiters are often the easiest types to discover, if something like that can really be considered easy. Because they have a strong gravity and are close enough to their parent star, they both orbit each other around a centre of mass that makes the star appear like it's wobbling. Depending on the mass of the bodies, the centre of mass can be within the parent object, or with objects of a similar mass, it could simply be a point in space. Wherever the centre of mass is located is known as the barycenter. One of the most extreme examples in our solar system is Pluto and Charon, which orbit around a point above Pluto's surface. In regards to Dimidium, astronomers could detect shifts in the distant star's light and confirm the presence of a large exoplanet because it's causing the star to wobble. This method of detection is called the radial velocity method, or Doppler spectroscopy. The discovery of Dimidium, made by the Elodie spectrograph in France, won the astronomers a Nobel Prize, and it was considered a major breakthrough for European astronomy. Since then, there have been many new exoplanet discoveries, and we know now that the galaxy is teeming with planets. This is where the Cheops mission comes in. It is already in orbit and sending back more than 1 gigabyte of data every day. Cheops orbits in what is called a heliosynchronous orbit, 700 kilometers up around Earth. In other words, Cheops is in a dawn-dusk polar orbit. That means that it travels around Earth along the twilight terminator line, with the sun powering up its solar panels on its back. Meanwhile, its gaze peers deep into space, protected from sunlight interference. Cheops' mission allows the telescope to study the smallest exoplanets we know, called super-Earths. They can be as small as our planet, but can also be as big as Neptune. The goal of Cheops is not to find new exoplanets, but to examine ones we already know about, to determine what they are made of and how they are formed. And that is very exciting, because it has the capabilities of discovering potentially habitable worlds. Planets that might have a similar size, orbit, and composition to our home. Cheops is much smaller than Hubble. It's only 1.5 meters across and uses a 32 centimeter mirror. However, it can see exactly what the designers had hoped for. And here is its first glance at the stars. Now, something about this image is very peculiar. All the stars imaged here are blurry, and no exoplanets are visible. No, this isn't a design flaw. Cheops is working as intended. The reason for the blurry image has something to do with the second method of exoplanet discovery, namely transit photometry. One of Cheops' key instruments is a very advanced photometer that can detect the tiniest amount of light variations on distant stars. If an exoplanet's orbit is aligned with us, it will transit the parent star so that it covers some of the star's disk from our perspective, in a similar fashion to a tiny eclipse. And that's what Cheops does. It monitors the amount of light it receives from a specific star, and then detects light variations from when a planet crosses in front of its disk, to see how much dimmer it gets. The reason the Cheops image is blurry is so that light from the star hits more of the camera sensor, increasing the number of pixels that get hit by the star's light. Through this, astronomers don't need to see the exoplanet itself, but this increased resolution allows astronomers to accurately record and study the star's light spectra itself, as well as any changes that take place from the exoplanet's transit. As you can guess, the bigger the planet, the more light it will obscure, and the easier it will be to notice a dip in light intensity. For small planets, however, this process is much more difficult to measure. And that's why Cheops is so important, as its advanced instruments and blurry images allow astronomers to better define the transits of those smaller, more Earth-like planets. Additionally, Cheops can measure a planet's phase curve, or how much light it reflects from its sun. When a planet is in front of the star, it will block light, but as it orbits around to the sides, it will reflect light back to us, which makes the star appear a little brighter from our perspective. Here, Cheops' photometer comes in handy again, this time to measure the increment in light variation. By comparing it to the light we receive when the planet is behind the star, when it's not interfering with the star's brightness, scientists should be able to isolate the spectrum of the light reflected by the planet. With that, they will be able to know the composition of the planet's atmosphere. And since they are investigating only the most promising planets, they can take multiple readings for a more defined measurement. But why does Cheops have to be in space? Can't we do all these readings from Earth? Well, just like the James Webb Telescope, telescopes here on Earth face two main hurdles. The first one is that we have night and day. That's a large section of a 24-hour period when no observations can take place. We might miss an important transit during that time. But even at night, the light a telescope receives is distorted as it travels through Earth's atmosphere. Photons hit several particles in different layers of the air, making the light flicker and wobble. Even if there are several methods to counter that, the readings would never be as accurate as they would be in space. That's why Cheops was launched into a sun-synchronous orbit. As I mentioned before, it will ride the terminator line of Earth. This not only allows it to receive constant light on its back for the solar panels to generate power, but it also means it can take a look at stars 24/7 without sunlight interfering with its readings. So, as you can see, with all the data Cheops will hopefully collect, it may just be a matter of time until we can confirm the existence of another planet like Earth, a planet with similar mass and temperature, with the presence of water and oxygen in its atmosphere, all the right conditions that harbored life here.
Coincidences aren't always coincidences. Imagine for a moment a game of pool. The balls are placed in a triangle and the pool player lines up the shot. He shoots. The balls scatter, but then, against all probability, they all start falling into the same hole, at the same corner of the table. What would you think if you saw it in that moment? Are you likely to chalk it up to probabilistic fluke? Or perhaps some skill on the part of the player? Or are you more likely to start checking under the table that no one's done something to lower one of the legs? Some things in the universe are so improbable, they really shouldn't ever happen. Think now about our solar system, and imagine a large mass came screeching into it, large enough and at just the right angle for its gravity to wobble one of our planets out of its orbit and to scatter that hapless planet into interstellar space, like the balls on the pool table, but a whole lot bigger. What are the odds that that mass would knock out not just one planet, but two? And that those two planets would head off in the same direction at the same speed, enough that once out in interstellar space, they would start orbiting each other. The odds are astronomical, but I suppose it's technically possible. And so it's not a complete surprise that the James Webb Space Telescope has found an example of exactly this going on in the Orion Nebula. In the space between stars, two planets are orbiting each other. Each of them has a mass similar to that of the planet Jupiter, so scientists call them Jupiter Mass Binary Objects, or JUMBOs for short. But the Webb didn't find just one example of jumbos, it found 40, representing almost 1/10 of all the wandering planets that Webb saw in Orion. That's not just unlikely, that's downright suspicious. So much so that it's time to start checking the legs of the universe to see what's going on. I'm Alex McColgan, and you're watching Astrum. Join with me today as we investigate jumbos and try to find clues to explain just what might have caused such objects to occur so frequently in Orion. One thing scientists all agree on: our models for the formation of stars and planets are certainly wrong. But in what way is still to be discovered. Jumbos were first seen by the James Webb Space Telescope in October 2023, when it turned its awesome high-resolution instruments on the Orion Nebula. It's possible jumbos exist in other places too, but they have remained undetected for now, probably as their relatively small size makes them quite difficult to spot, unless you're using techniques like gravitational microlensing, which is in and of itself a highly randomized way of finding new planets. Gravitational microlensing, or seeing the momentary increase in a star's brightness due to the relativistic effects of an object passing in front of it bending more of its light towards you, is an event so unlikely that Einstein thought we'd never actually catch it happening in nature, even though he theorized it was occurring. While technology has improved to the level that we can actually take advantage of gravitational microlensing as a way of spotting new planets, mostly by developing some wide-angle telescopes, which you can watch a video about here, you still need a jumbo to pass in front of a star before you can see it. It's not surprising that relying on such randomness has left a lot of planets slipping under the radar. We need a powerful telescope like the Webb to give jumbos a proper look. But when we did discover them, they were a total surprise, one that no one in the scientific community had seen coming. The ones seen by the Webb are relatively young, only 1 million years old, compared to our own Earth's 4.5 billion years. But the strangest thing about them is how they orbit. Instead of orbiting happily around a neighboring star, or drifting through the vastness of space like most rogue planets we've discovered before, jumbos orbit each other. They are binaries, gently caught up in the gravity of the other at a distance of around 200 astronomical units, or 200 times the distance between the Earth and the Sun. Frankly, this is baffling. Binaries aren't completely unheard of in our galaxy. In fact, they are relatively common. About 1/3 of all the stars in the Milky Way are binary or higher, meaning it's quite natural for orbiting bodies to take this configuration. However, the smaller you get for the size of your star, the less this tends to happen. 75% of massive stars are binaries. 50% of stars the size of our Sun are. For smaller stars, this number drops to 25%, and for objects smaller than a brown dwarf, which aren't big enough to ignite into fully fledged stars at all, and are only around 15 to 75 times the size of Jupiter, it really shouldn't ever happen. Jumbos ought to be impossible. There should be no reason their frequency should suddenly uptick to roughly 1 in 10. And yet, that's what the Webb saw. When it surveyed the space within the Orion Nebula, astronomers were excited to spot 540 different planetary mass objects much smaller than brown dwarfs, and of these, 9% were orbiting each other in these binary pairs. 2 were even circling in a triplet, which is really rubbing probability's nose in it. 9% is an astonishing number at this scale of mass. As soon as scientists realized jumbos were this common, they immediately recognized that our models for the formation of planets couldn't be correct, as there are only 2 explanations for where jumbos could come from. The early days of a planetary system are always chaotic. You've likely seen artistic depictions of molten Earth in its early infancy, with comets and space debris raining down on it. This space debris was far more common in the solar system's infancy, when dust coalesced into rocks, then into asteroids, and eventually into planets with enough gravity to pull everything in around them, causing cataclysmic collisions along the way. Sometimes that gravitational pull was such that it didn't smash 2 objects directly into each other, but instead pulled them out of orbit and left them careening into deep space. This can even happen to very large planets if the circumstances are right. For example, it is actually theorized by some researchers that our own solar system used to have one additional gas giant, which was bullied out of our solar system by Jupiter, or possibly Saturn, although the smart money is on Jupiter. Jupiter's gravity was enough to tug on this other gas giant until it was sent spiraling out into interstellar space. We've asked on this channel before whether there might be a Planet 9. We didn't consider that Jupiter actually might have given it the boot long ago. Regardless, the idea of a planet being sent out into interstellar space, even a large planet the size of Jupiter, is not that extraordinary. Indeed, it's believed that wandering planets of all sizes are fairly common. There could be billions to trillions of rogue exoplanets wandering around in the void of space between planetary systems in our galaxy, which, if true, means there are more flying around out there than there are likely orbiting stars. But the sheer number alone cannot account for that 9% ratio, so something else must be going on. But the alternative explanation for the formation of planets doesn't work either. This second theory states that in the aftermath of a large supernova explosion, or through the force of solar winds, hot matter is sent flying in all different directions away from the center of a nebula. Cosmic dust pushed outward this way is also pushed together, helping it begin to coalesce due to gravity and form new stars. But if stars can arise in this way, why not planets? After all, to push enough dust together to make a star, you at some point will have an object the size of a planet, right? But no, not on its own. While this happens in the nurturing planetary disk of a newly formed star, it turns out that without that extra gravity, an aspect of gas physics stops this theory from working in interstellar space, or at least for objects of that size. It turns out that something called the opacity limit puts a lower threshold on the size of objects that can be formed this way without a star. They either come together to form, at smallest, a brown dwarf, or they resist coming together at all. In other words, interstellar dust and gas go big, or they go home. It works like this. All objects have gravitational potential energy. When gas coalesces together due to gravity, it loses that gravitational potential energy. That energy has to go somewhere, obviously, so in nature it tries to radiate away as heat. This is all very well and good when the gas is spread out, but once more and more gas starts gathering in, as you might see when gravity is pulling in material for a planet, then everything gets cloudier and cloudier, or more and more opaque. This actually makes it harder and harder for this heat to radiate away, so instead things stay hot and energetic. This pushes back on any more material coming together. A delicate balancing act is thus reached, where hot gas that cannot quickly cool down pushes back too hard against any gravity for any planet to form. Stars get around this problem by having a little extra oomph in their formation. There is a reason stars tend to form in nebulas. This vestigial extra push is enough to overcome the hot gas's dislike of pulling together. But once you push past that barrier, you already have too much oomph to form just a planet. Now it's a brown dwarf, or something bigger, or nothing. The opacity limit sees to that. Which is why scientists are searching around for an additional ingredient, something that might explain how a jumbo might still form in interstellar space. To me, this explanation seems like the neater one. If somehow you could overcome the opacity limit, you'd end up with planets naturally arising out of interstellar matter. If two Jupiter masses formed close enough to each other, they would drift slowly together and could quite naturally take up orbits around each other with no star required. Nothing about this relies on crazy probabilities, as the first pool table leg planet theory asks you to believe in. There could even be planets smaller than Jupiter masses out there doing the same thing. Two Earth objects, or even smaller, just too tiny to be caught in the Webb's camera. But perhaps an old theory can provide an answer. In 2001, long before we had any idea jumbos might exist, a researcher called Alan P. Boss published a paper in the Astrophysics journal about the way objects slightly smaller than the mass of Jupiter could form from interstellar matter, provided that magnetic fields are active in the formation process, in effect jettisoning out the newly formed planet mass from the growing cloud that was about to become a brown dwarf, leaving the rest of the cloud to continue on its way towards collapse and stardom while preserving the smaller planet intact. The paper admits that it's conjecture and says that more work needs to be done to verify the idea, but I find it intriguing that the sizes in this theory match the reality of jumbos long before we saw them. Maybe jumbos weren't entirely a surprise after all. Is magnetism the answer to jumbos? It's too early to say. All we know for sure is that we know less than we previously thought. Jumbo's existence calls into question our models on the formation of stars and planets, and shows us more research is desperately needed. But then, that's half the fun of science. A theory is all well and good to have, but when you find something that throws off your theory, it's not a bad thing. It's an exciting discovery and an opportunity to get even better understanding of the reality we live in. What are jumbos? They are strange, Jupiter mass objects weaving a delicate dance on their own through space. But they might also be the key that unlocks our understanding of how stars and planets form in the first place.
You may have heard many news stories about all the thousands of exoplanets that have been discovered using the Kepler telescope. As of the 1st of July 2018, Kepler has confirmed the existence of 3,797 planets in 2,841 star systems, with 632 systems having more than one planet. But are any of these planets habitable? What are the chances of life being found outside of Earth? Are we alone in this universe, or can life be more prevalent than we think? And if there is life, where can it be found? I'm Alex McColgan and you're watching Astrum, and together we will explore known exoplanets in the Milky Way galaxy to see if any of them have the potential to harbour life. Now, we've not been able to actually image exoplanets in any kind of detail. In fact, this is the clearest real image we have of an exoplanet, taken by ESO's Very Large Telescope, which may make you question, if this is the best image of an exoplanet we have, how can we discover exoplanets, and how do we know life could be on one? To answer the first question, we have to look at how Kepler worked. Kepler is a space probe which constantly monitored about 150,000 stars in a fixed field of view using its camera. The field of view focuses on a patch of sky near the constellation Cygnus. This is what Kepler can see. The data it collects is sent to Earth and analysed to see if any stars dim periodically. You see, the concept is, if a star's planet passes in front of Kepler's view, the star will dim. If it dims, for instance once every 100 days, we can confirm that it is a planet and it takes 100 days to orbit. Kepler is really good at finding exoplanets. Before Kepler came into operation, these were the exoplanets we knew about. As you can see, most of them are many times the size of Jupiter. Since Kepler came into operation, we have discovered and confirmed the existence of thousands of exoplanets, with thousands more still unconfirmed. Remember, these are planets which have been discovered in only this patch of sky. There is still a lot more out there. Kepler unfortunately is no longer functioning how it used to, as some of the reaction wheels inside it are broken. However, the good news is that there is a new exoplanet finding spacecraft called TESS, which just came into operation a couple of weeks ago, which will cover an area in the sky 400 times larger than the Kepler mission. It is expected that during its mission it will be able to find more than 20,000 exoplanets. In order to determine details about an exoplanet, the distance from us to its star needs to be worked out using complicated maths. For stars within 400 light years away from us, we can use trigonometry and the orbit of the Earth to create a difference in angles. Beyond that, there is no direct measurement, So the best current method is by comparing a star's color spectrum to its brightness. The color spectrum of a star corresponds to what type of star it is. Once the color spectrum is known, scientists then know how bright the star should be. Comparing the apparent brightness, or the apparent magnitude, to the actual brightness, the absolute magnitude of the star, reveals how far away it is. This method is proven, as scientists have done this test on stars that are within 400 light years, and the results produce similar distances in both tests. Once the distance to the star has been determined, the amount the star dims can be used to see how big the planet is, its distance from the star, and the exoplanet's mass, based on the orbit of the exoplanet. Using other telescopes like Hubble, ESO, and eventually the James Webb and the WFIRST telescopes, these exoplanets can be studied to find out their composition, particularly of their atmospheres. The way this is done is again from the spectra of the exoplanet's light. To give you an example of how this is done, imagine white light shooting through a prism, producing what is actually a blend of colours spanning from violet to red. Light from a star shooting through an atmosphere produces a similar effect, except certain bands of light are not present. This indicates there is a certain gas in the atmosphere that is absorbing the light in that wavelength, not allowing it to pass through. The dips in this image shows what Earth's spectrum looks like as sunlight passes through the atmosphere. The dips show that oxygen is present, as well as water vapor, carbon dioxide and methane. These gases all absorb the sun's light at these wavelengths. Looking at the section of wavelengths and comparing them with other planets in the solar system, sulfur compounds can clearly be seen on Venus, and methane on Neptune is apparent. This means that as we study exoplanets in detail and determine their spectra, we can search for atmospheres that resemble our own. If it does, then the chances are that it could be a habitable world, and also that it may already harbour life. Inhabited planets could have telltale signs of life, like smog and pollution, which would be seen in the planet's spectrum. So, have any exoplanets like these been found? Well, out of the thousands of exoplanets that have been discovered, 16 of them are thought to be rocky planets and sit in the Goldilocks zone, or the habitable zone of their respective stars. Let's just remind ourselves of the ingredients needed for life as we know it. We believe that liquid water needs to be present. Liquid water is essential because biochemical reactions can take place in water. Water is also an excellent solvent that easily dissolves and carries nutrients and other compounds in and out of cells. Life forms on Earth are made primarily of water. In fact, our human bodies are more than 60% water. Life also needs sufficient protection from cosmic and solar radiation, which can break down and damage cells. On Earth, this protection comes from our magnetic field. There also needs to be essential chemicals found in the ground on Earth, and an energy source, which for us is the sun. So the Goldilocks zone is where, assuming other conditions are right, liquid water could theoretically pool on the surface. This zone is always different depending on the parent star and how big and hot it is. Looking at our own solar system, Venus might just be in the Goldilocks zone, as well as Earth and Mars. We already know that only 1 in 3 planets in our own solar system's Goldilocks zone can have liquid water, so just being in the right place is not always enough. The type of star is also important. Our star, although seemingly active on the surface, is actually quite stable compared to a lot of other types of stars. The Sun will likely be 10 billion years old before it burns out. On the other hand, the hottest types of stars will only last for millions of years in comparison. It is thought that this is not enough time for life to form around it, certainly not animal life that can communicate as we understand it. So we have a lot of filters we can now use to narrow down our search for habitable worlds. Out of the original 3,797 confirmed planets, 16 are terrestrial planets that orbit within the Goldilocks zone of their stars. However, the habitable zone of some stars means the planets are close enough to be tidally locked, meaning only one face of the planet sees its star. This proximity to the star also means the planet is exposed to a lot of solar radiation, sometimes thousands of times more than we are exposed to on Earth. In other words, out of those 16, only 4 are likely candidates to be Earth-like, although it is worth mentioning that exoplanets in systems like the TRAPPIST-1 system could still be habitable or have life even if all the planets are tidally locked. But the TRAPPIST system is worthy of its own video, so I won't expand on it here. These 4 exoplanets are Lyton b, Kepler 62f, Kepler 186f, and Kepler 442b. Realistically speaking though, we don't know much about them other than their size and mass. Our current technology isn't accurate enough to determine the composition of their atmospheres. One of the James Webb Space Telescope's missions is to study known exoplanets in greater detail, which is exciting as, in combination with the finding power of the TESS telescope I mentioned earlier, this next decade could be full of discoveries. But by using the Kepler data as a fairly decent sample size, can we estimate how many habitable worlds there could be in our galaxy alone? Ethan Siegel did a very interesting article, which I will link to in the description, where out of those 150,000 stars, the chances of seeing anything at all using the transit method is very small, less than 1% for a planet orbiting the distance of Mercury, let alone Neptune, which has a 0.001% chance of detection. This is due to the way planets tend to all orbit along a plane, and if it's not lined up, we won't see anything. Also, smaller planets are much harder to detect. Look how hard it is to see an Earth-sized planet compared to a Jupiter-sized planet. Taking all these things into account, Ethan Siegel placed a low estimate of 6.4 billion planets in their star's habitable zone in our galaxy, the Milky Way. This means at least one of them has to have life too, surely. Well, we really don't know how prevalent life is at all. And until we do some serious research and improve our technology, we have no way of knowing yet. Some people claim that all factors considered, the chances of humans being able to develop and live on Earth was 10 to the power of 10,123 to 1. In other words, extremely unlikely. How many factors actually are needed to be right for life to exist? Is it all over the place, or purely a freak coincidence here? Building on what we know already means the future is going to be very exciting.
Thanks for watching. We are now very close to our end goal of 1,000 astronauts on Patreon, and I can't thank you enough for having answered the call. The closer we get, the more it's looking like I'll be able to expand our content here and bring back Astrum Answers. So submit your video suggestions and questions over on Patreon. If you'd like to become an astronaut, you can join the Patreon with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.